In this video, we'll talk about the analysis section of the exemplar. So the first point available is that your raw data is sufficient, that it could support a detailed and valid conclusion. Now what does that look like? So here is the raw data, and there are repeat readings, 3 repeat readings per independent variable, and there are at least 6 independent variables. I would say absolutely no fewer than 6, because that will allow you to plot a good graph and to ignore repeat anomalies. Now, the next part is how you go about doing the calculations to turn your data into the nice linear graph that you expect to see, that will allow you to compute the number that you said you were going to compute in the research question. Appropriate and sufficient accuracy to enable a conclusion to the research question to be drawn that's fully consistent with the experimental data. So, we said that we were going to plot the mass against t squared in the exploration section. So what we're going to need is the mass, which we have, against the time squared, which we don't have. But this is the raw data. We measure the mass and the time. A thing to be aware of is that we've put the resolution of the measuring devices that we talked about in the exploration section up here in the header. And partly this is so as to remind us to make sure that we've put the right number of decimal places in the table itself. Now, plus or minus something in the same units as the thing you're going to measure, that's an absolute uncertainty. So this is an absolute uncertainty here, a length of 30.0 centimeters plus or minus 0.1 centimeters. That's an absolute uncertainty, and we can quote those to one significant figure. We can quote percentage uncertainties to 2 significant figures, and that's usually because we don't quote them as the final line answer. We quote absolute uncertainties. Percentage uncertainties are useful as the steps in a calculation, so we're allowed to keep an extra significant figure as what we call a guard digit, so as to make sure we don't end up with rounding errors, or to minimize the effect of rounding errors in the calculations. So the percentage uncertainty on L in this case would be 0.1 over 30.0 times 100%, 0.33%. I'm quoting it to 2 significant figures. So L here would be 30.0 centimeters plus or minus 0.33%. Now, we have absolute uncertainties. The absolute uncertainty, which is, the resolution rather, of the mass is 0.001 kilograms, i.e. we said we could measure a mass down to the nearest gram. So your values of the mass must also be quoted to the nearest gram. We said we could measure times down to 0.01 seconds, 0.001 seconds, so your time should be quoted down to 0.001 seconds. The average, similar. The half range, the same. The estimated uncertainty we're now going to talk about. Underneath your raw data table are going to be your example calculations, and the reason you have example calculations is you need to show that you have accurately done your analysis. And what that means is, for every calculation that you do, you pick an example. So I tend to pick probably the second line of data, and then I do that as my example. So here we go. Here's how you calculate an average. You sum the trials and divide by the number of trials. There it is. An estimate of the random uncertainty can be computed by finding half the range. So that's max minus min over 2. That's what that is. And then this estimated uncertainty column is the larger of the two values, the half range or precision. So this is the number you've quoted, which is an estimate of the spread, an estimate of the absolute uncertainty of the time, and you said you could measure that down to 0.001 seconds, so whichever is the biggest of these is the biggest contributing factor towards the uncertainty. So this is what we say is our estimated uncertainty. And you'll note this is an absolute uncertainty, so we quote it to one significant figure. So, in our example, for the second row, the precision is smaller, the resolution, that should say, resolution. The resolution is smaller than the half range, so the estimated uncertainty is the bigger of the two, which in this case is 0.01 seconds.